All right, so welcome to the second part of this workshop. So you just heard about the supply side. To have a viable ecosystem, needless to mention, you need both supply and demand. So now we'll switch gears to the demand side. And by the way, great job, supply side speakers and Carl. You guys are a tough act to follow. So again, the same rule book. We'll have 10 minutes for each speaker. You will receive a notification at 9 minutes, 30 seconds from Andrea. And after all the talks, we will have the mini Q&A panel. So with that, let us get started. Our first speaker is Keith Churchill from Bechtel. Keith, you're on.
Thanks so much. I really appreciate it. And I'll be sharing my screen and running the slides, I think was the goal here. So let's go ahead and put that up and make sure that we've got that moving forward. All good with the screen share?
Looks good.
Okay, thank you so much. Okay, when I started to put together the slide deck, I was looking through our image library, and I was trying to find a project that had the closest condition to the moon. And you know, incidentally, the project that stood out to me was this copper mine that we have in Chile. Not only is it extremely remote, but it's actually might be the closest project that we've ever done to the moon in terms of elevation. This project was completed at 3,500 meters above sea level in the most remote locations of the Andes Mountains, which provide a lot of challenges that you know are similar, but you know, not as extreme as lunar construction would be. But in terms of supply chain, in terms of personnel, the lack of oxygen, so many of those types of factors play into those types of projects, which we do fairly regularly within the company. If you're not familiar with Bechtel, you know, we do work in basically all sectors of construction, ranging from nuclear work, energy providers, you know, utilize us to build their facilities, whether that's power plants, LNG, so on and so forth. I mentioned mining and metals, which we do globally, a lot of very remote projects in that respect. And then we've got a significant presence in the infrastructure business, doing all sorts of projects ranging from transportation. We're actually working, you know, working on the ML2 platform in Cape Canaveral currently for NASA. Bechtel's been active in the space construction market recently, participated in the Break the Ice Challenge as a judge, and also we were a sponsor for the Mars Habitat Challenge. So we're definitely see the opportunity here, and I wanted to put this slide up on the screen, not just as an advertisement, but more as around what our business, you know, from a lunar perspective would be. What's our lunar business unit outside of the global business units? And you know, after hearing all of the discussions this morning, it just reiterates the fact that, you know, the lunar business unit is going to have to be a combination of all of these different business lines. There's going to be components of each and every one of these businesses that are going to have to contribute and rely upon each other as we start to develop the facilities on the moon. You know, the interdependencies between what's produced at the mining level to what's produced at the processing facility, you know, and they rely on the power, and how do we leverage the byproducts that were all discussed this morning are extremely important and are relevant to the discussions of not only what do we need, but then, you know, I think that if you turn that question around, what do we have and how do we use it? And I think we got to a lot of those discussions at the end of the last panel, you know, determining, you know, if we have iron, or if we have aluminum, or if we have the I guess the, you know, sort of non-common metals that we might see on Earth, how can we leverage them in ways that we might not be able to here because of the conditions on Earth, whether, you know, if we're talking about gravity, or we're talking about the loads that we're putting on, or the temperatures or pressure. You know, there's so many factors that are different here than they would be on the moon. And I think taking all of that into consideration is going to be really, really important as we become reliant upon ourselves as we start to expand on the lunar surface. Bechtel has been known to take on the most difficult, challenging projects in the most difficult conditions in the most remote locations. And this is an actual advertisement from one of our projects in and around World War II, where we were building a pipeline that was supplying critical fuel to the troops on the West Coast. And so you can see there that warning the workers that were applying for this project. Obviously the temperature range is significant. The mosquitoes and the wildlife and all of that are significant. And as I got to taking a look at this, I got to thinking about what would this translate to for lunar construction? How do we prepare for lunar construction? And what sort of workers will we need to perform this work? And it actually got me to take the next step in terms of saying, on this project, I would say that we put a lot of people on this project, right? We took a lot of people, put them up in the wilderness, put them in camps, got them food, all of the support that we have. And I think that as we start to expand in lunar construction, it's going to be quite the opposite. We're actually trying to do this with the least amount of people to start out with, and then work our way towards, having habitats that can sustain life for an extended period of time. So, where we went from the simplest, most manual sort of construction activities, now we're transitioning into the least manual, least labor intensive construction activities, leveraging autonomous equipment, leveraging robotics, and really trying to do the simplest forms of installation. And I will say that as we take a look at all of the pictures that were shown in the presentations in the earliest session, all of the different habitats, all of the the spheres for fuel storage and other storage. When I take a look at those things, I think about all of the pieces and parts and coordination and supply chain that have to happen to support those types of projects. So as I thought about, what do we need to build? First I had to kind of sit back and say, okay, what do we want to build, right? And we know that, we're going to have these, preliminary ISRU units, all of these support habitats and structures that are going to be built on the Earth and transported to the moon, but there's capacity limitations, right? And it was reinforced this morning where we plan on expanding to the point where we're sort of self-sufficient on the lunar surface. So what do we need to be able to do that? And as we talked about internally, what do we want to think about? What metals do we really want to use? Alumina really rose to the surface, and I think that it did was because of the fact that even though there's a lot of iron on the moon, or and sort of can be produced from the processes that we heard about earlier, there's no carbon on the moon, so there's no opportunity to really make steel. Can we use iron? Probably, but could we use aluminum? That would be produced from alumina that's a byproduct of some of the processes that we heard below. And I say that that's probably the one that we're most familiar with. We use here on Earth today, and we can leverage that to get some pretty predictable outcomes when it comes to performing design and construction activities for facilities. So if we're talking about energy production, that was a huge topic earlier, whether that's going to be nuclear or solar. I think that there's applications for aluminum to be used as supports, to be used as containment, and that translates into fuel storage or just storage in general. How do we build storage facilities? What are the components that we need to build those? All of the pieces and parts that go into building those tanks. Fuel processing, as we scale up the deliveries to and from the moon, and as we start to branch out maybe to mining in different locations, to Mars missions, fuel will be more and more important. And the more fuel that we need, the more fuel that we produce, the better facilities that we need to store and transport it. So all of the piping and all of the components that have to do that are going to be critical, and I mentioned launch and landing facilities. And then lastly, kind of the last step here is getting those habitats and those those areas that are, protected and shielded from radiation? How do we build those facilities in a manner that doesn't require significant pieces and parts to come to and from the moon from Earth, right? So how do we build these facilities differently than what we do on the Earth today? What are the approaches from a constructability perspective that we need to look at? I think that somebody mentioned earlier that we've got to think outside the box, and we can't just be restrained to the ways that we've done things in the past. But on the other side of the fence, there's some very complicated mechanisms, electronics that have to be, sort of produced somewhere. And I think that if we can start to really, think about what components can we, effectively build on the moon, fabricate on the moon, and put together on the moon, how do we reserve those trips back and forth in terms of the deliveries to and from for those critical things that require minerals that may not be found on the moon, or expertise that might not be available on the moon for things like pumps or instrumentation or computers or anything like that. So can we really reserve those for those critical storage locations on these lunar missions as they're coming from Earth? So as you sort of step back, the next slide was really intended to kind of show the different components, a lot of which were talked about earlier. I did want to mention, from a reinforcement perspective, and it's sort of going along the lines with the title of this program, is that reinforcement can come in a lot of different forms and fashions. What I've got shown here is through this traditional rebar. However, you could look at fiber reinforcement for certain types of applications, whether that be paving or road bases or simple structures. So can we really simplify the manufacturing process and not use as much material maybe in order to get the results that we need? We're going to need a significant amount of plates or something that equates to plates to provide shielding and support for the projects that we're looking to build. Pipes and other size members in terms of trusses, that was mentioned a lot earlier, pipes for supports for solar applications. I think that's, those structural members are going to have to be simplified, but they do have to be produced. And I don't think that's something that has to be overlooked. Yeah, once we have the raw material, that's great, but then we've got to be sure that we can produce the pieces and parts in the shapes that we need. So that's just another step in order to get to actual construction. And then energy transfer, whether that's through fuel transfer or that's through electric current transfer. Can we utilize aluminum wire? Can we utilize some of the other components and metals that were being produced by the processes that were discussed earlier as wire, so that we don't have to relocate or deliver that from Earth? And then lastly, I think the most complicated thing is fastening and connecting things, whether that's through welding or whether that's through physical fasteners or connectors like bolts or something that's designed on the moon. How do we simplify, the products that we need? What are the products that we actually need? How do we keep that list low enough to be manageable for manufacturing processes on the moon to support construction activities? So there's going to be challenges in terms of the equipment. Yes, there's going to be challenges in terms of those specialty type of pieces of equipment. But I think that the key here is, what are the manufacturing processes that need to be established on the moon after we are able to extract the metal to be able to support construction? I think that those questions are sort of to be determined, but don't forget and don't sell short the complexity of some of these facilities that are going to be needed as we scale up on the lunar surface. So I think I'm a little over, Antanu, but I appreciate the time. Thank you so much.
Nope, actually you're under time. That's good, and we have a lot of aluminum fans here. So, and also if I could direct your attention, Keith, to Q&A, and there are two interesting questions for you, if possible, if you could attend to them. And thank you very much. Very interesting talk. And also to all the speakers, if you could, if possible, if you could answer questions in the Q&A, because we won't have time to go through all of them in our Q&A panel. So thank you very much, Keith. That was very informative. And next we move on to Daniel Inocente from Skidmore, Owings, and Merrill. Daniel.
Hey, I'm going to share my screen. Is that okay?
Yep.
Okay. let me know when you guys see it.
Yep.
Okay, perfect. Good afternoon, everyone. It's a pleasure to be here and get this chance to share some thoughts about the future of design and construction as we're all exploring what ISRU development will mean for research, industry, and production technologies. So a little bit about myself. I'm currently a senior designer with SOM in New York, and throughout my career, I have been intimately involved in designing international projects across scales. As part of the design process, one of the things I focus on is developing integrative methods to address contemporary challenges in architecture, engineering, and construction. But I'm also passionate about space architecture and cross-sector research. At SOM, I've had the opportunity to initiate and lead partnerships with the European Space Agency and industry partners like Lockheed Martin. And these partnerships have really challenged me to think about different ways that architecture can play a role in an off-world context. But the theme of today's talk is potential uses for metals in extraterrestrial construction and not about skyscrapers, although many of the problems that we will likely confront when thinking about design, manufacturing, and construction on the moon or on Mars will have similarities to that of real-world construction, especially as the AEC industry moves more towards the using robotics, automation, and computational design technologies. These are a few projects that I've had the opportunity to work on during my time at SOM, and each one of these deals with issues of material use, constructability, sustainability, engineering, and most importantly, design. So design is one of the most critical aspects of thinking about developments, regardless of the environment or building typology. Design is all about performance, function, and the integration of qualities that range from technology to aesthetics. And aesthetics will be a part of future developments on other celestial bodies. So that's something we have to keep in mind. And as I move forward, in the world of architecture, structures come in all forms, types, and scales. And so one of the beautiful things about architecture is that there are no boundaries to thinking about the built environment. We can think about structures that are additively manufactured in large complex buildings that are made up of numerous discrete elements made from a wide variety of materials, like we just saw, and assembled in different working environments leading up to its final construction on site. And a lot of research has gone into construction on the moon, and many of these research efforts have been supported by NASA to leverage the expertise of industry, applying industry knowledge to the challenge of resource utilization and different ways of transporting, developing, and supporting infrastructure. You can see from this short list of examples that architecture really plays a critical role in developing ideas for future extraterrestrial bases. And I think what is important to keep in mind as we all continue to apply our skills to this challenge is that there won't be a single solution, but a myriad of ideas working together to sustain an ecosystem of solutions, much like on Earth. And so advanced manufacturing techniques are going to be very critical to this. These are two projects that were developed by SOM. So one of them, the one on the top, is a project where we're using polymer-based composites to 3D print structures, and the other one is using 3D printing concrete techniques to 3D print structures. But these make use of a wide range of skills. So everything from computer modeling to optimization using engineering models, and then finding ways of taking that information and sending it over to robotics for construction on top of building the infrastructure and the equipment necessary to build these things. And so what are the major drivers to think about as we continue developing ideas about extraterrestrial architecture, manufacturing, and construction? And for disciplines that will continue to evolve into this new territory, some of these are less intuitive. And so you can think about geography. This is going to be something that will differ as you think about different locations. Also building type, what are the kinds of structures? Are they occupiable? Are they for storage? Are they going to be used for specialty type activities? What dimensions or scale, the form factor, that's going to play a huge role. And then what are the premium drivers? So what drives the construction technique? Are you using, in situ 3D printing, or are you bringing elements that are prefabricated to the site and then you're assembling them? So in that case, you might imagine like robotics working together to assemble large pieces that are already kind of like produced as a product. And then of course, sustainability is going to be a big one, because when we start to develop this new territory, we're going to have concerns about ecosystems and how to use materials, intelligently and sustainably, and of course, construction costs, planning, and operations and maintenance. So all of these key drivers or key factors we have to continue to consider as we think about these challenges. So rebar, I think, is something that is being used quite a bit in the building industry. So in the building industry, rebar is one of the most critical elements used in reinforced concrete structures. And concrete alone is strong in compression, but weak in tension. And any structure will always experience a mixture of stresses, not just compression. So rebar provides concrete with a considerable amount of added strength compared to using concrete alone. And rebar can be used for a wide range of structural elements such as columns, floors, walls, and shells. And one of the things that we can start to imagine in the future is that rebar together with regolith type composites could actually be used intelligently to improve the efficacy of the material, the energy that you're using. And so this is a project by SOM where we're looking at how do you create formworks to create structures that minimize the use of concrete, but maybe maximize the use of metals. And so there's rebar in the structure, but because of the form and the shape, you reduce the amount of concrete, meaning if you have a trade-off in materials, that you can start to optimize certain fabrication or manufacturing techniques. And so that's one example. Another one that we can start to think about is things like steel nodes or metal nodes, not steel, metal nodes. And if we can print or fabricate these kinds of nodes in situ, then we can imagine a scenario where we have products or elements that can be assembled on site or can help support structures that are much bigger. And so this is an example from a project where we had a wide range of different nodes. But if you're 3D printing these, you can come up with any number of solutions, any number of unique cases, and they're all additively manufactured, so that's not an issue. Another application for metals can also be reinforced concrete shells. So if you have a thin shell that spans a long distance and tries to encapsulate a large volume, you can start to think about how do we use metals to reinforce this large regolith structure. This is an example project too from SOM. And so there's other ways of thinking about metals. Metals can also help contain large shell structures. And if you can build that large shell structure, you can optimize the way that you're using the metals. You can differentiate the metals or the use of material depending on where the forces are in the structure. This is an example for the Air Force Academy where we're using steel elements and we're differentiating the steel elements to respond to the forces. And so lunar regolith, is composed of minerals and glasses with many of the elements we need for construction. By volume, depending on where the sample is taken from, up to 90% of regolith contains silicate minerals and 20% oxide minerals. Regolith offers incredible opportunities for new types of structures. For example, there has been research conducted to study the compressive strength of sintered regolith with numbers reaching up to 30,000 PSI, which is 5 times stronger than Portland cement concrete. Other resources such as iron, aluminum, titanium offer potential applications to reinforce and develop composite elements as well. We should also think about lunar activities. So lunar activities, there's obviously a lot of exploration. We have to understand the composition of the regolith. And once we characterize the materials, then we can start to think about resource development. Where can we extract the materials in a much more efficient way? And then finally, what are the kinds of testing and operational techniques that need to be used to make use of those materials to turn them into products? And I know this is a slide with a lot of words, but just to get the idea across. And one project that we recently worked on where we tried to explore this idea of 3D printing metals for a space application was in collaboration with a company called MX3D in the Netherlands. And so this is a 3D print or additive manufacturing and engineering company. And they had already developed some really interesting methods and tools for 3D printing with metals. They primarily work with stainless steel, but they also work with aluminum and potentially other metals. And so we took this idea of what if we had designed, for example, like a habitat, a pressurized system, and then
Daniel,
we deliver
I'm
that
sorry to
pressurized
interrupt.
system. Oh, yes.
I'm sorry to interrupt. You have 30 seconds left.
Okay, no worries. I'm almost done. Thank you. And so we then deliver this pressurized system, and we 3D print the floor in situ, and we install it. And so we came up with a design process where we modeled, engineered, and then delivered that 3D file to MX3D for 3D printing. And the results were quite interesting. We did a lot of testing to make sure that the 3D printing was working, and we refined that process over a series of studies. And these are just some pictures of what the final product looked like. And so, yeah, just to conclude, I think this is going to require a lot of evolution in terms of disciplines. A lot of disciplines will come out of this. A lot of different industries will come out of this. And as we start to refine, thinking about, different elements that we can build, we might imagine a future where all kinds of structures are possible. Everything from thin shell structures to large structures that are made out of composites and metals combined. So it's going to be, I think, a combination of different materials and different types of structures working together. Thank you.
Thank you, Daniel. Some very interesting concepts. Thank you very much. So again, please put your questions in the Q&A, and if possible, specify to whom it is directed. So next, we move on to Sam Ximenes from XArc Astroport. Sam?
Okay. I'll get the screen up here. Have you seen the screen yet?
Yep. Could you put it in the slideshow mode, please? Good.
All right, so I'm Sam Ximenes. I'm with Astroport Space Technologies. My background is space architecture, and recently we've moved into civil engineering, trying to understand the civil engineering processes for constructing on the infrastructure under the surface. And our first application of it is going to be in the development of landing ports. And what we're looking at here is not so much the metal part of it, how to use metals, but how to use the actual regolith itself and solidifying the regolith and stabilizing it for building construction for the landing pad titles. What we do at Astroport is we develop space materials. We're building the ability to produce bricks, tiles, and rods, tubes out of pure basalt without any additives or reactive agents. We're also trying to get filaments out of the basalt, and we've got an additional process for 3D printing the basalt, but this one, that process involves a binder that goes with it. For the most part, though, our focus is on the landing pad construction, and we have a process for making that pad into a one-step process for laying down the tiles. Our goal at the end here is we want to actually not only be materials development and the construction, but also an operator of the landing ports when it's at a point where we have constant resupply and crew change out and logistics chain happening. That's the vision of the company. So our competencies are in refining. We have a couple of different melting refining technologies. One is an induction furnace that we use to melt simulant under simulant. And we have our own simulant that we work with here, sourced locally in Texas. We're based in San Antonio, Texas. We've been able to produce bricks and test bricks and coupons, and have been doing testing on those. We're actually right now in the process from another. This is actually part of a NASA contract we were awarded with. We have another contract from another government agency to produce rods and tubes and connectors for in-space manufacturing using lunar resources. We have our IP. It's this really kind of the driver here is this nozzle that we have that allows us to form the brick and place it. It melts it, forms it, and places it at the same time. And then additionally, we just received a license from NASA to commercialize the excavator of the Razor to see what kind of terrestrial applications we can use it for, and also get a moon-ready version of it done as well. It's more of a research license, evaluation license. So our core technology here is this melter, this printing system. It uses a combination of the induction furnace integrated with the nozzle with a hopper system. We've been able to test those bricks to high performance concrete standards greater than 40 megapascals. So we think we have a good solid material. The other thing we're doing is as I mentioned, we're doing the excavation technologies. We're developing a suite of tools to do the construction process itself, the site preparation that goes into the pad, sieving and leveling the site itself, and then also using that material with a hauler that it becomes the source material for the tiles that are being produced. So we have a couple of things we're trying to achieve as well, besides beyond the bricks. Our goal is to get to basalt rebar. Essentially, basalt rebar is used here on Earth as a building product. We want to get to geotextiles out of basalt. We've been able to fine print the basalt into almost a bendable fabric, and then you can see here at the bottom of the screen the test coupons on top of the size of the brick. We're moving from the 2-inch coupon to the 160 millimeter diameter interlocking brick would be our next phase. And we've also been able to look at the basalt into a glassy material and trying to polish it out into a reflective material as well. On the right side of the screen, you can see where we've been pulling the basalt. And this is just pure basalt into the rods, as these are our first test samples of that. We're working with different laboratories to do the evaluation of the characteristics of the fibers in the rods. So we have another process that we're teaming up with another company that has a way to take the metals and bind them with a PLA agent and 3D print to produce spools or filaments for 3D printers. And the license we're working with is to take that same process and apply it to space applications. Once the folks here that's on the call that can extract the metals out, we have a way to turn it into a filament. Of course, the PLA is the long pole in the tent producing PLA. We don't want to import it. We want to be able to get it, have it on the surface. That means a whole large infrastructure of growing biomass and greenhouses, and that whole thing behind it is way down the road. So we also took the basalt and with that same process and turned the basalt into a filament. We see here's the on the right again is the fine printed geotextile we're able to produce. Here's a simple model of a small scale habitat, and this is a version of we developing also a hang printer for large print surface areas. We can print from meters to hundreds of meters in size. This section here is the wall of the habitat you see over here on the right side. This is a honeycomb shaped wall for thermal conductivity, and over here on the left side is a full scale section of that wall being printed with this filament, this basalt filament, this simulant. So our roadmap here is to get. We're currently delivering the first prototype by June. We're at the point now where we're putting the bricks into vacuum to show that we can make these in vacuum. That should be done by June of this year. And then our next phase is to take the test. We're going to build a test bed, 10-meter diameter test bed, and to put the mobility platform and the razor and the mounting the nozzle on the heater on the mobility platform and test it out. We want to get to the lunar surface by 2026 with a first brick on the moon demonstration. So to the point of this particular section, the needs. We have done habitat construction, habitat designs, and 3D printed habitats. And this is a kind of a pretty picture of what's inside one of these habitats. There's an airlock there and a bunch of, a 3-story structure, and pretty nice. But how did that all get there? When you start printing these habitats, there's nothing more than shell. But the outfitting part of it is the problem we have with habitat printing. The secondary structures problem in 3D printing. How do you bring all this stuff in there? How do you get all the plumbing and all the MEP systems and the wiring and the electricals and even the furniture? We don't want to bring that all up. We need to find a way to take these metals, take other kind of materials and produce them up there, whether it's 3D printed or casted or whatever. That's going to be this is more of a problem than the actual 3D printing of the habitat itself, the construction printing. I think this is probably a larger problem than trying to figure out how to make a shell on the surface of the moon. You can see here just another image of the complexity of the outfitting these things. And if you all seen pictures of the space station, I'm so sure you have. You see wires going everywhere, and it's not a really pristine orderly environment. It's going to be messy, and it'll be the same thing I believe also with the first systems, the first habitats and research stations that are being built up there as well. What do you do? Do you haul all these big secondary structures to the shell and then you have to insert it robotically or with the aid of astronauts, or do you 3D print them somewhere at some other remote site and then haul them over there, or is it printed within the shell itself? Those are challenges to outfitting that the metals sector can help once we have the ability to get the metals out of the regolith and turn it into a filament or a powder or whatever your process is going to be to enable you to actually make a product of it. And I think that's probably my last slide. Yep, that's it. Thank you.
Thank you, Sam. It was great. And again, please post your questions in Q&A, and please I request you to keep your questions within the scope of lunar surface technology and development, nothing else. So with that, let me move on to our next speaker, Carrie Abramotti from Redwire Space. Kari?
Hello. Hi, all. I'm going to share my screen real quick. Okay, you should be able to see my presentation.
Yep.
My name is Carrie Abramotti. I'm a business development manager at Redwire Space. Our company, I'll give a quick overview of our company and then talk about some specific technologies that I think may be of interest to this group and talk about sort of where we see ourselves fitting into this economy and what we're thinking about and having issues with. So to start off, I just want to introduce Redwire a little bit for those who may not be familiar with our company. We were formed mainly through acquisitions over the past year and a half. And at our core, Redwire is a space enabling company that provides hardware development services and solutions around these focus areas that you see on the slide. I think the focus areas that are most relevant to today's conversation are OSAM and LEO commercialization, because a lot of those technologies, we're adapting for planetary exploration and long distance space travel. Here I have our locations. You can see we have a pretty big footprint across the country, as a part of the different acquisitions that we've performed. And I think the two companies that are, again, most relevant to you all and who you may have heard of are Made in Space, which is the company that I joined originally about 3 years ago, that later became part of Redwire. And that's located in Jacksonville, Florida. And the other is TechShot, which is located in Indiana. So you may have heard of those companies, and they have a long history of in-space manufacturing and specifically with metals. So just to give a quick overview of that history, throughout Redwire, we've manufactured over 200 objects that were physically manufactured in space to date. Many of those were the result of our additive manufacturing facility, which is a permanent facility located on the ISS that prints in space grade polymers. And those parts and pieces that we've printed have been for a variety of uses, and many of them have been for useful useful objects. You can see here on the right, you know, a bit of a support for a hurt finger, for example. We've printed wrenches and tools and other things of need on the ISS, and that's really where you know, our manufacturing history started, is, you know, understanding early on that we would, you know, for substantial sustained space travel, you know, on orbit and on the moon or Mars, we really need to have the capability to manufacture objects in situ, you know, using either resources and filaments that we've brought, or, you know, extracting the resources from a planetary surface. So the end goal has always been building towards that reality. And so here I have kind of an overview of the different manufacturing payloads that Redwire is building or has flown to the ISS. And as you can see, there's a variety of materials manufacturing, including metals and electronics. And so all of these were, you know, developed in-house through R&D and also through NASA and other government funding. And again, so you know, you may be wondering why I'm talking so much about the ISS and about LEO when this is a lunar workshop, but the reason is that all of these technologies, in one way or another, are intended to also be used on the lunar surface, either in a similar form, you know, as a you know, somewhat contained payload that can print and manufacture, you know, smaller objects that need, you know, that may be needed on the lunar surface, but also, you know, using these fundamental printing and manufacturing technologies and scaling and modifying them for use on the lunar surface, you know, externally for construction, things like that. That's where all this is headed. And you know, we have the basis of these technologies on the ISS, which is great because we have, you know, some sort of space qualification. It's not the same as lunar qualification, but you know, for most of these technologies, knowing it works in microgravity is a good you know, a good step, if not, you know, all that we need to understand, you know, that something will work in 1.6G. But of course, there's other, you know, lunar issues that need to be worked through. But this is really the basis of our technologies that we're looking for, you know, adapting for lunar construction. So I want to talk about two in particular that have to do with metals, and kind of just talk about where, in a little more detail, you know, what these can do and where we see it going. So first off, here you can see the Fabrication Laboratory, or Fab Lab. It's a single printing and furnace facility that can produce parts for a variety of human spaceflight activities. The metal parts that are produced at the facility are titanium 6-4 parts. And the way that the system works is that a part is printed in the upper module. You can see it's labeled in pretty small text, print module, using a titanium paste. We're actually working with the University of Louisville to create a titanium filament as well. And that first piece has some waxes and polymers in it and is soft, what we call a green part. And after that initial print, the astronaut places it in a vacuum furnace that goes first to about 550 C and burns off the waxes and polymers, which shrinks the part. And then we have what we call a brown part. And then the temperature is raised again to closer to 1300 C, and the part is sintered and the solid, and becomes solid with 96 to 97% density. At that point, the astronaut can put the part back in the upper module in the printer for millwork, which is primarily a cleanup and tolerancing activity, not, you know, traditional, more extensive millwork that you would see in the machine shop. And at the end, you have a final part like those you see at the bottom right, and all those parts were produced to be useful NASA, you know, spaceflight products, all from the NASA ISS parts database. So those are real usable parts that we manufactured on the ground during testing that already, you know, kind of aligned with NASA's needs. And, you know, the idea, obviously, I think it's obvious, is that these parts would be useful in case of a part failure, or if you're building a new system, you can manufacture these, you know, solid and important metal parts in situ. This printer also can print in polymers. So the print module and the furnace are, are standalone systems. It also has the ability to manufacture electronics. You can print a circuit board in the upper module, with a layer of polymer, and conductive inks can be laid down with the same print head, and there's an ability as well for pick and place for components. And finally, you can print traces and complete that electronic part. So this is a pretty diverse system that can do a lot of different types of manufacturing. And it's something we're pretty excited about and excited to continue developing and demonstrating. So right now we have a functional ground prototype. The next phase B is for a flight-like unit for testing and verification before a flight unit build that should fly within 2 years to the ISS for testing, 2 or 3 years. So this is one of our metals capabilities, and as you can imagine, this this exact system could be sent to the lunar surface for metals manufacturing. The second one has a lot of similarities, or some notable similarities. It's called Vulcan. This is a single platform for additive and subtractive manufacturing, and it prints metals using aluminum wire and filament, and it can also perform polymer printing and arc welding, and CNC machining. So it's also a very versatile payload. It's using a different type of metal for printing, but can do a lot of but it has a lot of those same types of flexibility. We've also tested other materials with the system, including titanium, stainless steel, and copper alloys. Probably something of note for this group is that we've also begun testing printing an iron that is contaminated with silicone, which should mimic some of the resources that we may be able to get from the moon. The results from those prints were favorable, but need more work and more testing to
Carrie?
Yep.
Sorry to interrupt. Just wanted to let you know you have 30 more seconds.
Oh no. Okay. I made this too long. All right. I'm gonna breeze past this. Just say that we have this other metal manufacturing capability. On this next slide, I highlighted RegISS, which is a regolith and polymer print system that flew to the ISS last year. This isn't too metal specific, but just wanted to highlight that we do have these other, regolith construction capabilities in-house. And on my final slide, I just wanted to bring home, where we see ourselves fitting into this market, and what issues and questions we still have. So as you can see, I've highlighted manufacturing capabilities in particular, and the ability to manufacture, goods and structures that may be needed on the lunar surface. That picture right there is actually for a wrist cuff for a lunar glove system that we printed in Louisville. That's actually for the NASA lunar spacesuit design. So, and we use Fab Lab for that. So we're kind of actively looking at what we can do now to prepare for lunar surface. But I think the one main question, and we've been talking about it all day, and I think the supply side, talked about this earlier today, but we're still trying to understand exactly what kinds of materials we're going to be getting from the moon, and we're looking for this community and others that are here to help us with that. We're doing our own R&D with different filaments and different materials, but really what we're honing in on is the actual manufacturing capability. So we're trying to understand what materials we can get and how we need to modify our manufacturing systems to be able to take in regolith derived materials and be able to build the goods and structures that are needed for the lunar surface. So I'll wrap it up there. And excited for questions and more conversation.
Thank you very much, Kari. Very interesting. You have a few questions in Q&A, if you could kindly answer them. So let's move on to our next speaker, Josh Trost from Relativity Space. Josh.
All right. Can you see my screen and hear me?
Yes,
we can.
yes.
All right, excellent. Thanks again for letting me talk today. Again, I'm Josh Brost with Relativity. I'm the Vice President of Business Development here, and been with the company about 3 years. And I'm always excited to talk about what we're up to. When most people think about relativity, they really focus on what it says on the chart. It says we build and fly entirely 3D printed rockets, and I think most people view us as primarily a rocket company. But really the reason that the company was founded was to completely change the way complex systems like aerospace products, starting with rockets, are manufactured on Earth, to create an industrial base that, again, on Earth makes much better products, but then that's also extensible to the surface of the moon and the surface of Mars. And that's all predicated on a belief that the only way to have a permanent presence on the moon and eventually on Mars is to be able to live off the land, if you will, and build permanent infrastructure using resources sourced locally, and extracting other resources to sustain human life. And so if you look at what we're starting with, we're starting with how do you make really complex things on Earth in a much simpler way. We started out with attacking a clear commercial market with our manufacturing tech of building launch systems. And if you look at the approach we're taking, we're really trying to take what was enormous physical complexity in traditional manufacturing systems and replace them with digital complexity. So switching from thousands of vendors producing millions of parts put together by thousands of people, we're trying to take all of that immense physical complexity and replace it with a simple feedstock going into a autonomous system that can manufacture complex things. And on Earth, that has the benefit of making products more capable and less expensive. But on the moon and on Mars, the only way you could possibly build complex systems in situ is to have it be a fully autonomous system. And so I'll click on this video quick, which shows us printing the second stage of our first rocket to fly, which is scheduled to actually leave the factory very soon to go on to do some integrated testing, all leading up to a flight later this year. But you can see in this printing process, we're producing a fairly complex structure that includes a common dome, stiffening ribs, all integrated as a single part. Even you can see, partway through, we start printing the down-encumbered tubing that carries the propellant from the upper half of the second stage down to the engines. As we've gone forward, we've continued to enhance the capabilities of this print system, really driving for increased autonomy. And what that means is a few different things. First, it's working on having a in situ inspection system that verifies drop by drop that the metal that you're depositing meets the requirements that you expect. Because on the moon, there's not going to be the opportunity to do a post-manufacturing inspection. You really need to get it right the first time. On Earth, we similarly want to make sure that our printers are operating at a very high utilization and very reliably to minimize our costs. So there's a very clear synergy there to solving problems for the moon that are important on Earth. And then also, it's really working on the overall characterization of the melt pool, of the control system behind it, of the sensor suite, all those things that integrate together to make this a very capable printer. If you look at a second stage tank such as this, it's about 7.5 feet in diameter. It's something a little, roughly around 20 feet tall, that is used to store liquid oxygen and liquid methane. And if you start to think about what kinds of permanent infrastructure will be required on the moon for people to stay, propellant storage will be a critical system that's required. Water storage will be a critical infrastructure capability, as will printing long live liners for habitats, as could be, printing large structures for surface mobility systems. And so having a very flexible manufacturing system becomes incredibly important. On Earth, we use this to print out of a aluminum feedstock. And again, given the amount of aluminum that is contained within the regolith, we see a very natural path to converting that regolith into feedstock that we could be used. To be clear, our company is not focused on that conversion of the regolith. We're really focused on how do you use that feedstock once it's in a form that we can accept. But we are continuing to work on our printing process to make it more and more flexible to be able to accept additional weldable metals with varying levels of quality coming into it to make it a very robust and flexible system. So again, this is just what our Stargate production system looks like on Earth. And it's easy to look at this and say, well, this printer is far too large to send to the surface of the moon. But actually, almost everything that you see is just a collection of COTS parts that are used to position the print head in the right location and to create the print envelope that we need. What really makes this the world's largest 3D metal printer is the print head combined with a proprietary set of sensors that provide the closed feedback loop that we need. And then an enormous database of materials properties that we've developed over time that have helped us correlate our print quality to both our in situ measurements and our controlled inputs. That the actual packaging of a moon or a Mars-based system would obviously look very, very different, but the technology that underlies this is directly applicable and extensible. So I'll wrap up pretty quickly. I think, again, thinking about why relativity exists and what we're trying to do, we really were founded believing that the future is interplanetary future where people are living and working on the moon and on Mars. And we were started to solve some of those fundamental manufacturing problems that are required to make it possible. We really think that, again, as I mentioned at the beginning, the only way to have a sustained presence is to have a fully automated industrial base, which is built upon 3D printing. And that's why we're really prioritizing our investments in that autonomy at this point in time on Earth and demonstrating it with rockets. And then again, as I mentioned earlier, kind of the core of our company is looking at how do you build a completely new version of an industrial base that then can be extended to make a permanent presence offers possible. And so that I'll wrap up, and I look forward to the questions.
Thank you, Josh. Interesting as always. You have a question from fellow panelist Daniel in the chat. If you could kindly take a look at it, he can put it in the Q&A. Next, we move on to Bryant Walker from Keystone. Bryant?
Yes, that's correct.
Okay. Do you want to share your slides, or do you want us to drive it?
You're
Andrea.
actually sharing his slides? Yeah.
Okay. Great. Thank you.
Thank you, Andrea. Hi, I'm Bryant Walker from Keystone Synergistic Enterprises. I'm filling in today for Mamour Hussain, who has been attending as a pretty regular member of your group. So Mamour is actually on vacation in Sri Lanka this week. So I'm filling in for him. So I may not have all the background that some of you have in history here with the organization, but I'll try and let you know a little bit about our company and our interests here. Next slide, please. Andrea, next slide, please. Thank you. Our primary capabilities are in three areas: wire arc, metal AM. We use a pulsed arc system, robotically driven. Laser wire, metal AM, which is again robotically driven, and then some hybrid 3D scanning inspections that we have developed to give us very precision inspections of non-contact inspections, obviously, of very complex parts, and to utilize and integrate that into our additive manufacturing methods. So we do, in our past experience, we've been doing this now for about 20 years. Our total metal tooling has been, we've made a lot of large parts. I'll show you a couple of examples, and very large components. Lately, most of that work has been in making nozzles for NASA. And so we are specializing in AM metal structures. Not sure why I've got a black spot in the middle of my screen now, but there we go. We also utilize laser equipment. Matter of fact, we're looking at integrating our pulsed arc and pulsed laser systems to create a system that will allow us to deposit at fairly high deposition rates, as well as very low deposition rates with a lot of detailed capability with the laser. So the integration of those into a single system, we think, will be somewhat unique. And then we utilize the inspection system, the 3D scanning, which is basically a structured light inspection system, to be able to not only pick up very small, very fine detail, but also the larger whole field inspection and integrate those to produce either a hollow or solid models that we can then utilize. Next slide, please.
Can you see your next slide?
We cannot.
Next slide, yes.
You need me to take over?
That one. Hold on. What's going on? Let me try it again. Apologize for the technical difficulties.
No worries.
Andrea, can you take over? I'm having some technical difficulties, please.
I'll take care of it.
Thank you. I apologize.
There we go. Thank you. Slide before that, please. Yeah, these are some examples of some of the parts that we have made fairly recently. Along the top, you'll see various types of large tooling. For example, the part this is about a 6 foot by 4 foot. This part here is approximately 6 feet in height. A lot of complex structure internally. This is more of an airfoil shaped configuration. And then you see a very large simplistic dome that's shaped. It's about 4 feet in diameter. On the lower side, we've been making lately nozzles for NASA, in which we deposit the parts out of nickel-based superalloys and then machine in the cooling channels. And that's followed by then a closeout utilizing the laser technology without utilizing any filler in the joints, or excuse me, in the channels. That allows us to produce a very complex nozzle. These have been hot fire tested by NASA and to confirm TRL-6 readiness. Next slide, please. Here's an example of not only the ability to make them, but also to repair them. As you can see on the far left upper photo there, we had an unexpected machine damage that into one of our nozzles that was quite expensive. So that we really went at trying to repair the nozzle. And we were utilizing our iterative deposition processing with both the wire and pulsed arc and pulsed laser. We were able to deposit and restore the metal to produce a repaired nozzle. Again, in this case, it was, and we've used several alloys, one of which would be like a Haynes 230. We've used Inconel 625. We've also used the higher strength alloys that NASA has been developing lately. Down below, you'll see the steps that we go through. We start out on the left-hand side with producing the backbone or the nozzle liner, then machining that, rough machining, and finishing it to produce the channels. And then from there, we close out the surface without any filler in the channels to then produce the regeneratively cooled nozzle. And we add the manifolds, top and bottom, and then hot fire test at NASA. We've done many of these now out of different alloys, Monels, and in addition to the high strength nickel alloys. And we've done them all the way up to 40 inches in diameter. So we've been had quite a bit of success here with this process, and we're looking to now apply that knowledge to how we can apply these types of processes to use on the moon. So next slide, please. So some of our lunar applications that we're thinking of would be like making truss structures for solar arrays, metal structures for habitats, and making tooling to locally required to facilitate manufacturing. And then, of course, large chambers and vessels, as was spoken of in the last presentation. And then metal structures for launch pads. You see all of those is very well inside of the capability that we have here on Earth. It's just now transitioning that to space and doing that on the lunar surface with the materials available from Regolith. Also, being able to repair, in situ repair, we think is a pretty important step here. And we think that's is something that we will very much want to do, particularly in space. And not only the repair, but also the how do you join? That's another facet that we have a lot of experience with, and that is solid state joining methods. I don't show that on this particular slide, but it's one that we neglected to put on, but it's one that we have a lot of experience with, because in a vacuum environment, being able to join metals just by use of friction and diffusion would be much easier than it is here on Earth, actually. So we think that's another challenge that we'd like to use our experience to then transition and demonstrate for use on the moon. So some of the local challenges that we see, of course, is availability of wire, suitable wire of the right chemistry, so that the products that are needed can be made. Understanding what are the specifications and requirements. That's another unknown, obviously, at this point. But considering this environment is considerably different, we think alloys can be re-engineered and redesigned, maybe to make them more simple and more utilized on the moon. And of course, achieving high levels of autonomy to reduce astronautic intervention with the equipment is very important. So we spent a lot of time doing that. We've looked at various methods of utilizing machine learning and in situ inspection methods, so that we can now eliminate much of that in practice from a technician, so that the in-space requirement is really not there to do that. So
Brian,
we know the importance of
sorry to
that.
interrupt you, but I'm afraid you only have 30 seconds left.
Thank you. Some of the other challenges, of course, would be partnering in ways that are mutually beneficial. And then right now, additive manufacturing for making very large structures is just at its infancy, really, on the Earth. And so trying to expand that to create a commercial base here from which we can draw R&D funds to continue our development is proven to be a bit of a challenge. So how we might partner together with other entities of interest here and with NASA is of a high priority to us. So thank you for your time, and we look forward to any discussion.
Thank you, Brian. Great talk. Very interesting. So we are at the end of our speaking section of this panel, and we have about 10 minutes for some questions. So one question I have for all panelists, and let me start with Keith first, is how can NASA make it easier for you to build structures on the moon, both programmatically and for building infrastructure? To what level NASA has to reduce the risk and things like that for you to feel comfortable going after the moon? Keith, and then others.
Yeah, so I mean, I think the biggest challenge right now is the fact that a lot of the autonomy that is going to be required to perform the work on the moon doesn't really exist even terrestrially right now. And I think that that's one of the biggest challenges that I see is just going from this environment where we're, used to installing things by hand, used to doing a lot of manual installation. There's a lot of I guess, really complicated sort of installation activities that happen on any construction site. I think that working on ways that we can reduce the complexity of the installations, reduce the complexity of the facilities that we're looking at to support those autonomous type of installations is going to be critical. And thinking about it in that way. And I think that, another thing that really needs to be addressed is thinking about the codes and standards for how we design these facilities and where we base our assumptions and our design calculations are going to dictate. I think it was kind of referenced this morning around what materials can we use and what are the right applications for the materials that can be produced. So I think those are two things that I see as extreme difficulties that we need help from a multifaceted audience.
Thank you, Keith. Daniel?
I'm sorry, can you repeat the question?
Yeah, so the question was, and this was to all the panelists, how can NASA make it easier for you to build structures on the moon? What NASA has to do to make you feel comfortable going after the moon?
Yeah, definitely. It's like if a client comes to you and they ask you for a certain project, they have to develop the criteria. So I think it would be really good to understand what are the needs, what kinds of exploration needs there would be for astronauts, whether it's like just being able to store equipment or actually making it habitable, which is much more difficult because as soon as you have humans involved, the stakes are much higher. So we have to understand that, and also what kinds of I guess mechanisms would be in place to bring different partnerships together between industry players, because one side of the architecture coin is we're really great at designing things and integrating things, but when it comes to means and methods, we need to partner with the right folks to actually build what it is we're imagining. And so in that case, there needs to be a capabilities really supported, like 3D printing, construction in situ, resource extraction, all that has to be in place for us to build things. And so hopefully, NASA will continue to evolve that.
Thank you, Daniel. Sam, what's your take?
Yeah, couple things actually. I'm going to echo Elliot's mantra about power grid. We need to get the power up there. These are power intensive processes. And the other thing is settling on the cargo lander. It really has a big impact on the way you set up, initially the equipment you bring up there and how that whole ConOps. It goes into what it changes from the Starship to a Blue Origin to a Dynetics lander dramatically. So once we settle on that, and this is mostly for the first missions, that's why that's important. So we can understand what that ConOps is and what those mass requirements are as well. So essentially the infrastructure support, the comm system that would need to be put in place as well.
Thank you, Sam. Kari, what's your take?
Yeah, probably a reiteration of what we just heard, specifically around requirements. I think something we run into across the board is, not having a firm ground to start on. And on the moon in particular, there's so many unknowns, from the lander to the power availability. I think at our company, we have a lot of different options to approach these things, but we don't, until we know what is going to be there and what we're going to have, it's just sort of a baseline power, mission duration, material, for our manufacturing process, like what material ranges can we expect and what quantities. Like once we get that information, we can really begin to tailor our systems and our proposals to, to that reality. So I think that's kind of a reiteration, just, from our own perspective of what we need. But I think, in the next couple years with some upcoming CLIPS missions and other, and other R&D work going on across the industry, I think those questions will start to be answered. But, any way that could be sped up by NASA or, just clarified, it would be immensely helpful.
Thanks, Kari. Josh.
Yeah, I think I'll echo a lot of what was already said by the other panelists. I think it's kind of two things in my mind. It's the infrastructure, the power, as mentioned by Sam, that enables each one of these solutions is obviously a super critical part. But to me, what I don't want is a ton of requirements telling me exactly how to provide a solution. What I want to know is what are the solutions NASA needs, what are the global capabilities they need. And really it's about seeing a demand signal that says, if I build this, will they come? Is there will there be a user for the capability that I'm already investing dollars in developing and extending to the moon?
Great. Thank you. Bryant? You're muted.
Yeah, I'd like to reiterate the importance of understanding requirements, because clearly that drives everything. And once we understand, what's good enough, because clearly we don't need, at least I anticipate anyway, that a lot of the metallurgical development that we put into alloys here on the Earth may not be needed on the moon. And at least we can probably get by with more simplistic alloys. And so that's a guesstimate on my part, but it would seem logical. So understanding what NASA thinks some of the requirements would be, I think would be quite helpful. So we can literally start designing alloys from the elements that are readily available and utilize some of the technology that has been discussed today on how to process that material and produce it in powders and wire format and so forth. We need a little bit more help with understanding requirements and specifics, so that would give us more of a direction there.
Thank you, Brian. We have 2 minutes left. And so the next question to all the panelists, and if you could answer in 30 seconds if possible, what terrestrial spin-offs do you see from your lunar technology development endeavors? Keith?
So mine really relates to taking, I guess, on the challenge of the labor shortage here in the United States and abroad is anything that we can build that operates autonomously is going to help us improve the way that the construction industry is viewed and really take us up to the next level in terms of technology on Earth. And I think that'll help negate some of the labor issues that we're having in the industry.
Interesting. Great. Daniel, thanks.
Thank you. I would say, I think thinking about like the grand societal challenges of sustainability, this is something that we could easily address with making use of the constraints and technologies that are being applied to space. So I mean, the kinds of spin-offs, I could go on and on about them, but things like, more optimum construction for composite structures, or thinking about different design processes, or just becoming much more integrative with the manufacturing process. So that there's just a number of things. I think it's a great question to ask and maybe worth a longer discussion.
Yep,
thank you.
I understand that. Thank you. Sam? You're muted, Sam.
We're involved with the Air Force AFRL and Space Force rocket cargo program, and this is the point-to-point delivery of rocket cargo from anywhere in the globe under an hour. So we're looking at space pads on demand, essentially, for when you land one of these rockets in a remote area where there is no infrastructure. You can put this system in there in that place.
Interesting. Josh? Oh, Kari, sorry. Sorry. I went in the order.
Yeah, to add to Sam's point, I'd say, there's a variety of different military uses, specifically in the Navy, on ships. A lot of these on-demand, part and manufacturing generation can be used there. And also as a kind of extension of Keith and Daniel's points, I think developing new simplistic methods for construction can filter through the terrestrial construction industries. There might not be a huge reason to simplify certain construction practices because the labor is not, it's not too difficult, or, the labor is available. But once you have no labor or one laborer, I think the methods that we come up with will eventually filter back to terrestrial markets.
Thanks, Kari. Josh?
Yeah, we're actually starting with the benefits on Earth first, and then trying to extend them to the moon. And so, right now we're building rockets that we can build for less money. We can build them faster. They can be more reliable and more capable because of this tech that is also an enabler for lunar activity. So I think we're in a kind of an exciting sweet spot where we get to use the benefits for an Earth business first and then extend them.
Thank you. And Bryant?
Yes, we're thinking that that really the more we can focus on autonomy, and particularly the tools that would drive that, artificial intelligence and machine learning methods to allow us to be able to make our process more autonomous, just that simple, and that would be very applicable to many processes. So that's where we see a lot of our focus in the future.
Thank you very much. So again, thanks. Great talks, great discussion. And that concludes this panel, demand side panel. And then I think we have a break now, and we will get back together at 3:30 p.m. for a combined panel discussion. So if all the panel members could stay on for a combined panel discussion, that would be great. Thank you. So we will see you at 3:30 p.m. Eastern in about 7 minutes.